Welcome to our animated journey into the world of semiconductors and logic gates. Today, we'll break down how tiny components like diodes and transistors form the backbone of modern electronics. Semiconductors are special materials that can conduct electricity under certain conditions, making them essential for building electronic circuits. From your smartphone to your laptop, semiconductors are everywhere, quietly powering the digital age. In this video, we'll explore how these materials work, why they're so important, and how they enable the logic operations that drive computing. Let's get started by understanding what makes semiconductors unique. Semiconductors are materials with electrical properties between those of conductors and insulators. Silicon is the most widely used semiconductor material. Its ability to control the flow of electricity makes it ideal for electronic devices. By adding small amounts of other elements, we can change how silicon behaves, allowing it to switch and amplify electrical signals. This property is the foundation for building complex circuits. In the next scenes, we'll see how semiconductors are used to create diodes and transistors, the building blocks of logic gates. Make semiconductors useful, we introduce impurities in a process called doping. Doping adds atoms to the silicon crystal, creating either an excess of electrons n-type or a shortage p-type. This process allows us to control how electricity moves through the material. By carefully arranging n-type and p-type regions, we can create components that behave in specific ways. Doping is a crucial step in manufacturing electronic devices as it determines how well the semiconductor will perform in circuits. Diode is a simple semiconductor device that allows current to flow in only one direction. It's made by joining n-type and p-type materials together, forming what's called a p-n junction. When voltage is applied in one direction, the diode conducts electricity, but if the voltage is reversed, it blocks the current. Diodes are used in many applications, such as converting AC to DC and protecting circuits from voltage spikes. Their one-way behavior is fundamental to modern electronics. Let's take a closer look at how diodes function. When a positive voltage is applied to the p-type side, electrons and holes move toward the junction, allowing current to flow. This is called forward bias. If the voltage is reversed, the electrons and holes are pulled away from the junction and the diode blocks the current. This is reverse bias. This simple principle is used in countless electronic circuits to control the direction of current. Transistors are the next step up from diodes. They're made by combining three layers of semiconductor material, creating either NPN or PNP structures. Transistors can act as switches or amplifiers, making them incredibly versatile. By applying a small current to one part of the transistor, we can control a much larger current flowing through another part. This switching ability is what makes transistors the heart of digital logic circuits in computers. Transistor has three terminals: the emitter, base, and collector. By applying a small voltage to the base, we can control the flow of current between the emitter and collector. This makes transistors perfect for switching applications. In computers, billions of transistors work together to process information, turning electrical signals on and off at incredible speeds. The invention of the transistor revolutionized electronics, paving the way for modern computing. There are two main types of transistors: NPN and PNP. In NPN transistors, a small current entering the base allows a larger current to flow from collector to emitter. In PNP transistors, the current flows in the opposite direction. Both types are used in different circuit designs depending on the desired behavior. Understanding the difference between NPN and PNP is key to designing effective electronic circuits. Logic gates are the building blocks of digital circuits. They use transistors to perform simple logical operations like AND, OR, and NOT. By combining these gates in different ways, we can create circuits that perform complex tasks, from basic calculations to running entire computer programs. Logic gates process binary signals, ones and zeros, making decisions based on the input they receive. Let's dive into the most common types of logic gates and see how they work. The AND gate is one of the simplest logic gates. It takes two or more inputs and outputs a 1 only if all inputs are 1. In other words, the AND gate acts like a strict filter. Every input must be true for the output to be true. This gate is used in circuits where multiple conditions must be met before an action is taken. For example, both a password and a fingerprint might be required to unlock a device. The OR gate is another fundamental logic gate. It outputs a 1 if at least one of its inputs is 1. Think of it as a permissive filter. If any input is true, the output is true. OR gates are used in circuits where any one of several conditions can trigger an action. For instance, a security system might sound an alarm if any one of several sensors is triggered. NOT gate, also called an inverter, has just one input and one output. It flips the input. If the input is 1, the output is 0, and vice versa. This gate is essential for creating more complex logic circuits. NOT gates are used whenever a signal needs to be reversed. For example, if a light should turn off when a sensor is triggered, a NOT gate can invert the signal. NAND gate combines the functions of AND and NOT. It outputs a 0 only if all inputs are 1, otherwise it outputs 1. NAND gates are called universal gates because you can build any other logic gate using just NAND gates. This makes them incredibly important in digital circuit design. Many computer memory and processor circuits rely heavily on NAND gates. NOR gate is similar to the OR gate but with a twist. It outputs 1 only if all inputs are 0. Like the NAND gate, the NOR gate is also universal, meaning any logic function can be built using only NOR gates. NOR gates are widely used in digital systems, especially in memory and control circuits. XOR gate, or exclusive OR, outputs 1 only if the inputs are different. If both inputs are the same, the output is 0. XOR gates are used in circuits that need to detect differences such as error detection and digital addition. Their unique behavior makes them essential in arithmetic and communication systems. XNOR gate is the opposite of XOR. It outputs 1 only if the inputs are the same. XNOR gates are used in circuits that need to check for equality, such as digital comparators. They play a key role in systems where matching signals is important, like data verification and security. Logic gates are built using combinations of transistors. For example, an NAND gate can be made by arranging transistors so that current flows only when all inputs are on. Each logic gate has a unique transistor arrangement that determines its behavior. By connecting many gates together, we can create circuits that perform complex operations, forming the basis of all digital devices. As technology advanced, engineers found ways to pack thousands, even millions of transistors and logic gates onto tiny chips called integrated circuits. These chips are the brains of modern electronics, enabling powerful computers and smartphones. Integrated circuits have revolutionized the way we live, making technology faster, smaller, and more affordable. Digital circuits use binary signals, ones and zeros, to represent information. A high voltage represents a 1 and a low voltage represents a 0. Logic gates process these signals, making decisions based on their inputs. This binary system is the foundation of all digital technology, from calculators to supercomputers. Truth tables are a simple way to visualize how logic gates work. Each row shows a possible combination of inputs and the resulting output. By studying truth tables, we can predict how a circuit will behave in any situation. They're an essential tool for designing and understanding digital systems. Combinational logic circuits use multiple logic gates to perform specific tasks. The output depends only on the current inputs, not on previous states. Examples include adders, multiplexers, and encoders. These circuits are used in everything from calculators to digital watches, performing calculations and data processing in real time. Unlike combinational circuits, sequential logic circuits remember past inputs. They use memory elements like flip-flops to store information. This allows them to perform tasks that require timing and order, such as counting or storing data. Sequential circuits are found in devices like clocks, memory chips, and microprocessors. Flip-flops are basic memory elements in digital circuits. They can store a single bit of information, either a 1 or a 0. By connecting flip-flops together, we can build registers and memory units that store larger amounts of data. Flip-flops are essential for creating sequential logic circuits and enabling computers to remember information. Adders are combinational circuits that perform arithmetic operations. The simplest adder, called a half adder, adds 2 binary digits and produces a sum and a carry output. More complex adders, like full adders, can add multiple bits together. Adders are fundamental to all digital systems that perform calculations, from simple calculators to advanced processors. Multiplexers, or MUXes, are circuits that select one of many inputs and send it to the output. They act like electronic switches, allowing data from different sources to be routed through a single line. Multiplexers are used in communication systems, computers, and many other digital devices to manage data flow efficiently. Encoders convert information from one format to another, usually from multiple inputs to a smaller set of outputs. Decoders do the opposite, expanding a small set of inputs into many outputs. These circuits are used in data transmission, memory addressing, and display systems, helping organize and interpret digital information. Timers and counters are sequential circuits that measure time or count events. They're built using flip-flops and other logic gates. Timers are used in clocks, alarms, and scheduling systems, while counters keep track of events like button presses or data packets. These circuits are essential for organizing and controlling digital processes. There are different types of logic gate technologies, called logic families. The two most common are TTL transistor logic and CMOS complementary metal oxide semiconductor. TTL circuits are fast and robust, while CMOS circuits use less power and are ideal for battery-powered devices. Each logic family has its own strengths and is chosen based on the needs of the application. Propagation delay is the time it takes for a signal to travel through a logic gate or circuit. This delay can affect how quickly a digital system responds to changes. Engineers work to minimize propagation delay to make circuits faster and more efficient. Understanding delay is important for designing high-speed electronics. Power consumption is a key consideration in digital circuit design. Logic gates use power whenever they switch states. CMOS gates are popular because they consume very little power when idle, making them ideal for portable devices. Efficient power management extends battery life and reduces heat in electronic devices. Noise margin is the ability of a logic gate to tolerate unwanted electrical signals or noise without making errors. High noise margin means the circuit is more reliable and less likely to malfunction. Engineers design circuits with sufficient noise margin to ensure stable operation, even in noisy environments. Fan-in refers to the number of inputs a logic gate can handle, while fan-out is the number of other gates it can drive. These factors affect how circuits are designed and how signals are distributed. High fan-out can slow down circuits, so designers balance these parameters for optimal performance. Some logic gates have special output types like open collector and tri-state outputs. Open collector outputs can be connected together for wired logic, while tri-state outputs can disconnect from the circuit, allowing multiple devices to share a line. These features are useful in complex digital systems where many components communicate. Programmable logic devices, or PLDs, are chips that can be configured to perform different logic functions. Examples include PALs, GALs, and FPGAs. These devices allow engineers to design custom circuits without building them from scratch, speeding up development and enabling rapid prototyping. Microprocessors are complex chips containing millions of logic gates and transistors. They execute instructions, perform calculations, and control devices. Every action your computer takes, opening a file, playing music, browsing the web, relies on the rapid switching of logic gates inside the microprocessor. Memory chips use arrays of logic gates and transistors to store data. Each bit of information is held in a tiny circuit, allowing computers to remember programs, files, and settings. Advances in memory technology have made it possible to store vast amounts of information in small, affordable devices. Digital circuits use logic gates to process binary signals, while analog circuits handle continuous signals. Most modern electronics use a mix of both, but digital circuits dominate computing and communication. Understanding the difference helps explain why logic gates are so important in today's technology. Moore's law predicts that the number of transistors on a chip doubles every 2 years, leading to exponential growth in computing power. This trend has driven rapid advances in electronics, making devices faster, smaller, and more capable. Logic gates and semiconductors are at the heart of this technological revolution. Semiconductors and logic gates are found in almost every electronic device you use. From smartphones and laptops to cars and appliances, these components make modern life possible. Understanding how they work helps us appreciate the technology we rely on every day. Looking ahead, researchers are exploring new types of logic gates using quantum mechanics. Quantum logic gates can process information in ways that classical gates cannot, potentially leading to powerful new computers. While still experimental, quantum logic represents the next frontier in semiconductor technology. As transistors and logic gates get smaller, engineers face new challenges like heat, interference, and manufacturing limits. Overcoming these obstacles requires innovative materials and design techniques. The quest for smaller, faster, and more efficient circuits continues to drive research in semiconductor technology. Semiconductors are also vital in renewable energy technologies such as solar panels and wind turbines. They convert sunlight into electricity and manage power flow in energy systems. As the world shifts toward clean energy, semiconductors will play an even bigger role in powering our future. Modern communication systems, including the internet and mobile networks, rely on semiconductors and logic gates. They process signals, encode data, and ensure reliable connections. Without these components, global communication as we know it would not be possible. Let's review what we've learned. Semiconductors are the foundation of modern electronics, enabling the creation of diodes, transistors, and logic gates. Logic gates perform basic operations that power everything from calculators to supercomputers. By understanding these components, we gain insight into the technology that shapes our world. In conclusion, semiconductors and logic gates are at the heart of the digital age. Their invention and development have transformed the way we live, work, and communicate. As technology continues to evolve, these tiny components will remain essential, driving innovation and shaping the future of electronics.